Log on, tune in, find out. Another good idea from Cambridge.
I'd like to introduce Sinan Yildirim. He'll be talking about forward smoothing and online in changepoint systems.
Hello. My talk will be on forward smoothing and online in changepoint systems. So first, the definition of a changepoint system. A changepoint system switches randomly between a number of models in time, and each model is assumed to be a hidden Markov model. The switching times are called changepoints, and portions between successive changepoints are called segments, and the HMMs are restarted at the beginning of segments. Here you can see the change points like 44, 152, here, and different models are labeled with colored with different colors. Like this is model 1, this is model 2. There's a transition from model 1 to model 1 here, model 1 to model 2, model 2 to model 1. Here's a more mathematical definition. We can define a changepoint system with three processes x, z, and y. X and z are latent processes, and y is the observation process. X is a Markov chain with two components, dk and mk, and dk is the duration the changepoint has spent in the current segment, and mk is the active model in the current segment, and this xk defines the underlying structure of the changepoint system. And given the underlying structure, that is the locations of changepoints and numbers of models which are active on those segments, then I can define then zk and yk are used to define the HMMs on those segments, and they are defined via the initial density for the state, and the transition density and the observation density. And those densities can be different in different models, which this fact is indicated by the superscript and here. Here's an example where we use changepoint systems, a real-life example, and it is the GC content in the DNA of human chromosome. As you know, the raw DNA data contains only 4 different letters. In here, we partition the 24 megabase region into 3 kilobase windows, successive windows, and for each window we calculate the proportion of letters that are G or C, and we get such a plot. And it is assumed that the chromosome is separated into segments, and the GC content over a segment is assumed constant and observed in noise. So it fits suitably a changepoint system. So Fernhead and Vasiliev in 2009 developed a changepoint system for this data, and in this changepoint system, the important point is that the observation is a Gaussian random variable with a mean and variance, and that mean and variance is constant during a segment, and these are the latent variables z. And the mean and variance are generated from a normal inverse gamma distribution with those parameters, and it stays constant, which is shown by this Dirac measure. And the set of unknown parameters, or parameters, let's say, is the mean of this inverse gamma distribution, say the variance parameter. And this is the probability that a new segment starts when I am in model 1, and these are two common parameters, alpha and beta, and this is the raw stochastic matrix that tells me about the transitions from one model to another. So in these kind of models, for accurate detection of change points, one needs to know theta. And our main goal is estimate theta given the observation. But when data is huge, there are batch methods available, but they can be too slow. So we need for online methods like recursive maximum likelihood, online EM, etc. And if possible, EM is preferred over recursive maximum likelihood in general. So we seek for an online EM algorithm for the maximum likelihood estimation. The EM algorithm, in the expectation step, we calculate the Q function, which is the expectation of log joint density with respect to the posterior density of all the latent variables given the observation. And in the maximization step, we maximize that function. And the maximizer is our new estimate. And if the densities in the HMM belong to the exponential family and some certain expectations with respect to the law of Zn given Yn and Xn are available, then we have those additive functionals. And what is interesting here that when we have these additive functionals, the EM algorithm becomes calculating those additive functions and applying a maximization rule. So what happens when we have additive functionals? Then we have the advantage to calculate them online in an online manner using a method called forward smoothing. Forward smoothing recursion uses a decomposition of this expectation. It introduces an intermediate function that is t, and this expectation becomes the expectation of this t function. What is more interesting here is that this t function can be calculated with a recursion, which we will call forward smoothing recursion. And this is the forward smoothing recursion. Hence, the expectation can be computed online, and this opens the door to our online EM algorithm. So in the online EM algorithm, running averages of those expectations are computed. And we introduce a stochastic approximation to the forward smoothing recursion by using our previous estimates for the parameters. And in the maximization step, the maximization step is now at every time step. And this, theta 0 to n-1 indicates that the required laws are computed sequentially. That is, using theta k-1 at time k. So remember our change point system here, and assume that these are unknown. So we have got 10 parameters, 2, 4, 6, 8. I say not 12 but 10 because this is a raw stochastic matrix, as you know. And here are the estimates by using online EM algorithm. It's a long data sequence of length 500,000, and we can see that our online EM converges quite successfully. Admittedly, this is very long data. This is a very long data sequence, but online EM can be applied to short data sequences as well. The way to do it is to replicate the data many times and treat it as it is the original data and apply online EM. So here you see the results, the estimates versus number of passes over the data. And you can see that most parameters converge after like 30 passes over the data. If I compare it to the offline EM, classical batch EM, you can see that we need at least 1,000 iterations, 1,000 passes over the data. So it can be beneficial to use online EM, even for short data sequences. And remember our real data, we applied our online EM for estimating the parameters of the model of the change point system to model that real data, and we got such results. That data is also too short for only one pass. So the results are the estimates versus the number of passes. and you can see that 30 iterations, 30 number of passes are enough for the all parameters to converge. In all of those algorithms, we use actually a particle filter approximation because calculating the exact posterior is not possible in practice. Here's a comparison between our forward smoothing method and the path space method in literature. The forward smoothing method. So first I'll talk about the particle filter approximation. This is the path space approximation, and this is the approximation to the filtering density only. So at time n, I'm just gonna finish 2 slides. So at time n, online VM via forward smoothing needs only the filtering density approximation, and the path space method needs the path space approximation. Therefore, the path space method suffers from path degeneracy. So SMCFS online EM algorithm, that is our algorithm, has better stability properties, and you can see it. This is my last slide. You can see it from this figure. These are the 100 estimates superimposed. This is for forward smoothing, and this is for the path space method, and these are the box plots. You can see that our algorithm has much less variance, and you can see also from this relative variance that the relative variance path space over forward smoothing is approximately 30-40. So okay, I'll skip this. Let's go.
Okay, any questions?
I'm confused as to why your online method would work better for a short sequence. Like, can you give some intuition why that's faster than just doing batch? Yeah.
Because you do your estimates at every time step.
Okay. But you
So
could.
in the batch VM, you calculate the whole thing first, the expectations for the whole data, and you do your estimates. So I can say that if the data is homogeneous enough, then doing estimates in small portions, if you think about it, doing estimates in small portions is more
So it's like you're doing little
it's
M
more
steps.
useful. Yeah.
It's like you're doing little M steps within the E step rather than.
Sure. Yeah.
Any more questions? Take one more. Okay. Okay, I guess we'll break for lunch now and return at 2. Just to remind everyone, the room with the posters are open, so you can have a look at the posters during lunchtime as well.